now starting. All attendees are in listen-only mode.
Hello dear participants, good afternoon and good evening. It's a pleasure to welcome you today as part of Power Quality community to this APQI webinar. Power quality related issues have significant economic as well as safety impact for various end customers, including industries, commercial establishments and buildings. The widespread use of power electronics equipment, especially nonlinear loads nowadays, leads to a change of load profile in a premise. The changing load profile is often a major cause of power quality issues, leading to further deterioration of safety, availability and reliability. Majority of the end customers are still not familiar of various power quality problems and do not have a way to quantify. Decision makers' ability to adopt a high power quality approach by adopting lowest first cost principle. Asia Power Quality Initiative or APQI as to build awareness and capacities on issues related to power quality. This initiative has local chapters in as many as 7 Asian and Southeast Asian countries. APQI is currently in its 6th year. This Pan-Asian platform, supported by national support network partners, continues to carry out activities towards capacity building and awareness raising amongst various stakeholders. We also work to facilitate regulatory and standards initiative in respective country. We provide a neutral platform for exchange of knowledge and best practices concerning power quality. Our website www.apqi.org is supported by Leonardo Energy Europe, and it is the single largest resource for various discussion papers, application roles, research and data on power quality in all the countries we work. We work with a focus on shared learning, transparent exchange of information and active engagement in the field. Power quality issues have significant economic consequences for various end customers like industries, commercial establishment and buildings. And they are increasing day by day due to increased use of power electronic equipment, load switching, sensitive equipment, etc. In fact, addressing power quality and adopting a high power quality approach is all of our responsibility. And therefore, we welcome you all on behalf of APQI India to this webinar, High Return on Investment for Industries, Commercial Buildings from Investments in Power Quality, along with case studies. This webinar brings together 3 industry experts as part of our national support network partner to explore the business case for customers to improve power quality at their premise. We have some eminent speakers today will be joining us. Mr. M.R. Srinivas, he is the edition expert and senior manager power quality from Schneider Electric. He has over 15 years of experience in PQ domain. He has been awarded as edition expert by Schneider Electric and been part of various innovations related to power quality in his company, and also applied a lot of patents for some good ideas. Our second speaker will be Mr. N.K. Jain, Director, N.K. Jain Consulting Engineers. He has wealth of experience over 40 years in designing, installation, testing, and commissioning of electrical distribution systems. He has successfully completed more than 450 projects of various sizes, especially in IT and data center areas. He is fellow life member of Consulting Electrical Engineers Association of Maharashtra, SEMA. And our third speaker is directly from the industry, Mr. Jitendra Jain. He is the General Manager of Usha Martin Limited. He has over 20 years of experience and works in the capacity of head engineering. In addition to engineering, he looks after energy, risk management, safety, environment, and Kaizen cells also at his company. I sincerely hope you will experience a good discussion in today's session and look forward to your active participation in future too. Thank you. Now I hand over you to Mr. Srinivas.
Good afternoon, guys, and good evening to everyone. This is M.R. Srinivas from Schneider Electric. Today we'll discuss about in-power quality. One of the major topic is harmonics. Today we'll discuss how exactly harmonic is going to have some impact on the reliability, on the cost incurred by current customer. And also we have some case studies with, that we can discuss for different applications. We have some case study on buildings, some refineries, and so on and so forth. So before going to the case studies and practical things, let's go briefly about why exactly harmonic is there, harmonic is required. What are the driving factors for harmonics in industry applications? There are three driving factors. There are three pillars that drives harmonics. Number one is the tariff. Many supply authorities they have imposed tariff on harmonics. That means if harmonic levels is beyond some level, maybe IEEE 500 standard or some other standards, there is a penalty on this aspect. Second pillar is the CO2 emission. If harmonic is beyond certain limits, a consumer will have more energy consumption because of so many reasons. That we'll discuss in detail how exactly it happens. The third, but the last but the very critical topic is reliability. How exactly harmonic will impact reliability, and how exactly the downtime is increased and significantly loss for the customers. So we club these three is called TCR, or we can say it's a total cost reduction for customers. So we're going to focus one by one, tariff, CO2, and reliability, and we're going to discuss on case study as well. So here we have some of the places where in India, for example, I don't have data from APAC countries, but anyway, I hope similar trend will be in APAC as well. Right now in India, we have few states, supply authorities, utilities, they already impose or are trying to implement some harmonic regulations at the metering point. They come and do the study at the metering point with their instrument, their consultants, contractors, and they verify if harmonic is beyond certain percentage level, there's a penalty imposed. And there are some private supply authorities who also have their own regulations on harmonics. Yeah. There's a tariff sample I just took it from one of the utilities in south part of India. He says if total current harmonic distortion is beyond 8% at the metering point. Metering point is a point where utility is having their estimator for recording energy pattern of the consumer. So as per this tariff, it says if the TSGI, the current distortion is beyond 8%, the penalty is 1/4 of energy charges. No significant. So the point is 25% of energy charges, so the penalty is a huge revenue for consumer. it may be 25 today, but tomorrow it may be 5-10%. The point is, utility companies are focusing. The vision is clear to make sure to implement these harmonic regulations. The only debate will be on the numbers, how many percent penalties should be imposed for the consumers. Well, we just touch upon basics of harmonics, just touch upon fundamentals before we go to the practical aspect of it. Why harmonic has become a big topic? If we convert entire globe as a single transformer, okay, let's say 100 kVA transformer, entire globe, 60 kVA is flowing in semiconductor devices. Semiconductor means it could be variable speed drives, maybe some converters, inverter applications, so on and so forth. This is up to a survey done by relevant some companies. 60% of the electricity is going into semiconductors. Whenever the power goes to semiconductors, we can expect a lot of harmonic coming out of the semiconductors. That's why harmonic has become one of the top first list in the list to discuss and go forward to solve the harmonic issues. Maybe in 3-4 years down the line, you can expect 60% will become maybe 80 or 90%. So what are harmonics? What you're seeing in the screen is a pure sine wave. It's got frequency, RMS value, peak value, so on and so forth. We'll give you a name for this. We'll call it as fundamental frequency, maybe 50 Hz or 60 Hz, any frequency depending on the country. The name given for this sine wave is the fundamental sine wave. Well, you cannot see this sine wave anymore in any industry. You can see only in this PPT or maybe in some laboratory. Suppose if we have one more frequency, one more AC sinusoidal frequency, which has two cycles. In one cycle of 50 Hz, 60 Hz, it's called second harmonics. No, there are two cycles in one cycle of fundamental, it's called second harmonic frequency. Similarly, if you have a sine wave, pure sine wave whose frequency is 5 cycles in one cycle of 50 Hz, it's called fifth harmonic frequency. So similarly, we have fifth harmonic, seventh harmonic, 11th harmonic, so on and so forth. So the harmonic is nothing but a pure AC whose frequency is multiple of fundamental. When you say multiple, it has to be integral. It is a whole number because we don't find non-integral harmonics in the industry except in few cases like arc furnace and so on and so forth. The question is how exactly a pure AC will become something else. How exactly the waveform will be distorted. The top one, the fundamental frequency will add up to harmonic frequency. In this example, I have 5 fifth harmonic here going on just below fundamental frequency. These two waveform will add up instantaneously. You'll get the waveform which is non-sine wave. This is an example of fifth harmonic frequency. If you have seventh harmonic, this is what it looks like. It's something more distorted. If you have 11th harmonic, this is what it looks like. This is a waveform of classic 12 pulse converters where 11th harmonic is dominant. Invariably, in any applications, you can find 5th, 7th, 11th is quite common to find. 5, 7, 11th is a major contribution of the harmonic spectrum. So when you have this 5, 7, 11, you're going to have this completely out of sine waveform. Now imagine we design an induction motor or design equipment, any machines, assuming pure sine wave. Let's say 0.11 kV or any kilowatt, but we assume pure sine wave to design the machine. But if you apply a waveform which is non-sine wave, it can perform well. So it will malfunction, it may fail, it may work with more stress, so on and so forth. Well, just a little bit of from where harmonic is coming from. Harmonic source, there are 3 types of harmonic source. The load will give harmonic current to system, like non-linear loads. And we have a voltage converter, that's transformers. transformers when you operate in saturation, beyond saturation point, harmonic will come into picture. Alternators or generators. Generator, if the winding pitch is less than the pole pitch, then you will definitely get harmonics from alternator as well. But our main concern is the harmonic from load side, because we cannot solve the harmonic coming from generator or transformer unless we design the machine perfectly. So today's discussion we'll going to discuss only on the harmonic coming from the load side. Just to divide the loads, so we have two kinds of loads. We just to make our life easy. We say linear loads and non-linear loads. So linear load, let's say I have two bus. You can see two bus here. One bus going in highway, and the straight highway, very high speed, 100 miles per hour speed, no gear changes. It's comfortable journey. It's called linear motion. Let's say one more bus going in the city, in a crowded city, in that manner. So always don't change the gears, and clutches, so on and so forth. So it's called non-linear motion. Similarly, in electrical system, a linear load means if you apply AC voltage to any black box, if it does AC current, it's called linear divisors. So any black box that carries whose response is exactly is equal to the cause, it's called linear divisors. The example: resistance, capacitance, inductance. When you apply AC, it draws pure AC. So example of linear divisors. So non-linear divisors means you apply AC voltage, but if it draws something pulsating current or non-AC current, it's called non-linear loads. So example will be all semiconductor devices used in converters, inverter applications are all non-linear devices. Yeah, so we just brief about the number of pulses. You know, we again divide non-linear load into number of pulses. If let's say we have a half-wave rectifier, we apply at the input side, we apply a single phase AC voltage here. If it draws one pulse of current in one cycle of voltage. So in a device, it draws one pulse of current in one cycle of voltage. It's called single pulse device. So example of single pulse device are half-wave rectifier. So two pulse device, let's say we have a bridge rectifier. You apply a single phase AC, but at the input side, you will get two pulses of current in one cycle of AC voltage. It's called two pulse device. So technically, you can have only two pulses in one phase. So that means if you have three-phase system, you can have 2 into 3. You can have 6 pulse converters in three-phase system. That's how 6 pulse converter come into picture. So this is what about the number of pulses. So it's very important for us to know the number of pulses because the harmonic spectrum depends on number of pulses. Harmonic orders depends on number of, what kind of load is this. The classic example of two-pulse converters are SMPS devices, SMPS loads that is used in all the laptops and computers and your LED lamps, so on and so forth. Some rules, it's sort of mathematics, what kind of pulse will give what kind of harmonics. So we have any two pulse, the formula is Kp plus minus 1. Any two pulse device will give more 3 and 7th harmonic. 6 pulse device will give 5th and 11th harmonic as dominant in the spectrum. 12 pulse gives 11th, 13th, and so on and so forth. So higher the number of pulse, lower the harmonic spectrum would be. So in other words, one of the ways to solve the harmonic issue is by going high number of pulses in the design. For example, they used to have 12 pulse, 24 pulse in the olden years. They used to have 24 pulse converters for steel applications or cement factory plant applications. So that was very expensive, but it used to work. Harmonic was reducing drastically. So one of the key things in harmonic is the sequence. Sequence in harmonic is critical for us to understand how exactly the harmonic will affect on the various equipment. Sequence plays a critical role in terms of how a machine will behave or misbehave with harmonic in the system. So we have fundamentally three sequences in harmonics. One is called the anti-clockwise rotation, is called positive sequence or plus sequence. We have clockwise rotation of vectors in three phase in harmonics called negative sequence vector harmonics or minus sequence harmonics. And we have one more sequence called zero sequence, where we have harmonic in three lines but without any phase angle difference. So we have positive sequence, negative sequence, and zero sequence in harmonic. This is a small table to understand the sequence in harmonics. We have just write down the harmonics from 1 to a. One is the fundamental, the normal frequency, and we have 2, 3, 4, 5, and just write down plus minus 0, and repeat same thing plus minus 0 here. Anything under plus is called plus sequence, anything under minus is called minus sequence. If you look at this table carefully, harmonic number 3, frequency 150 Hz in 50 Hz system, and multiple of 3 are zero sequence in nature. That means 3, 6, 9, 15, 12, etc., etc. Any harmonic multiple of 3 is called zero sequence in nature. Fifth harmonic is minor sequence. In many industries we see fifth harmonic more. So we want to understand how this sequence will influence the performance of induction motors, generators, so on and so forth. All right. So here we come to practical aspect of harmonics, effect of harmonics. The first effect of harmonic will be heating. Heating will increase CO2 emission and reduce the network efficiency, and it won't incur the energy cost for the consumer. So how exactly heating will have the network with harmonic in the system. So there is a phenomenon called skin effect. Let's say I have a copper conductor with a copper bus bar. We apply DC voltage for this, so electron will flow across the conductor equally. Not even an atom is left to flow the current. So electrons will flow equally across the conductor surface. So if you apply 50 Hz or power frequency, the center part of the conductor is not being used to flow the current. That's because of self-inductance in the conductor. So this is called skin effect. The skin effect means the current will tend to flow toward the surface of the conductor. So therefore, resistance of the conductor will increase with high frequency because the tendency of the current to flow towards the conductor surface. If we apply, let's say, fifth harmonic current, 2 Hz current, this is how it looks like. The speed is 5 times speed, and the center part of the conductor is not used at all to flow harmonic current. So harmonic will flow towards the surface of the conductor. That means you're going to have less area to flow high frequency harmonics. So as per theory, we can assume resistance of a conductor will increase with frequency, but in linear motion, linearly. That means if let's say we have a resistance of 1 ohms at 50 Hz, we can assume it will be 5 ohms at fifth harmonic frequency, and 7 ohms at 7th harmonic frequency, so on and so forth. So the 5 times increased resistance is significant to create heat loss in the conductor. This is thermal image we have taken at one of the shopping malls where we had a lot of fancy lighting systems in the mall. Apparently, we had this fancy lighting on only one phase, that is line number 3. So we made sure we told customer to verify, make sure the current RMS value of current is equal in all 3 lines. But only in line 3 we had significant harmonic current. So in couple of hours time we found the line 3 is having 56 degrees centigrade temperature. We did verify the termination everything was intact, but because of harmonics we have more temperature on one of the phase here. These are switchgear that is feeding UPS input side. You know, the UPS is rectifier, 6-port rectifier. I can see that the temperature on the conductor is 194 degrees centigrade. It's almost double the boiling point of water, and it's very dangerous. It's already, the insulation is breaking down and it's discoloring, so on and so forth. So the loading on this circuit breaker was just 60% of its capacity. Even then, the thermal temperature was significant on higher side. This is a cable from same UPS, but output of the UPS is going to all the computer nodes in the building. What you can see five cables here, 3 in green, 2 in red color. The 3 in green are line 1, 2, and 3 line conductors, and the 2 red are neutral conductor. The customer used double neutral because neutral was having a huge current because of zero sequence harmonics. So this complete cable assembly was in a panel in AC system. So the cable, neutral cable of 50 plus degrees centigrade with AC on. If you imagine AC is off, let's say for a couple of hours, maybe for 3-4 hours, it is going to catch fire. So it's very dangerous. Customer didn't know this. This is a problem in the cable, problem because of harmonics, but he was running the plant, building for more than 2-3 years with high degree of risk. So we come to induction motor. How exactly harmonic will influence the efficiency of induction motor? Let's assume this is an induction motor. Has 3-phase input. There is an induction motor and there is a mechanical shaft here that's coupling the load on the right hand side. We'll assume we have input supply, maybe 400 volts, 3-phase, 50 hertz. If you apply this input voltage, you will get some speed and torque on the rotor that will turn the load. Fifth harmonic, you remember, fifth harmonic is minus sequence, that means it's clockwise rotation. If any fifth harmonic harmonic is there in the same network where this motor is installed, the fifth harmonic will come and go into the induction motor, but the speed is 5 times speed and clockwise compared to the fundamental one, and it creates minus torque in the rotor that is transferred to the mechanical load. So the net effect will be low speed. The induction motor will have low speed even though the load is not actually changed. The mechanical load is still there, is not modified. So the harmonic will try to tend to reduce the motor speed, because of which induction motor will try to draw more power just to overcome this negative torque from the harmonics. So we have case study in refinery where this is HLD. We have a generator, 21 megawatt generator we have, and we have a 11 GA bus on both sides with bus couple on condition. There is a 12 pulse drive, 4.5 megawatts drive here, that's connected to 11 kV supply through 3-winding transformer. Harmonic from this drive is coming and is distributing to all the loads like this. So this is a voltage waveform that we measured at 11 kV bus. It's full of harmonics, and this voltage harmonic is driving current into incomer to 3.3 kV, where we have a lot of induction motor. Customer had a significant motor failures at 3.3 kV. He was saying they're replacing motor ball bearings, they're replacing the winding in the motors at least once in 3 months, 4 months, or so and so. So we measured harmonic current flowing to the induction motor, creating a negative torque on the induction motor, and it's eventually causing failure, premature failure in the motors. Here's some sample of harmonic current measured. Harmonic current measured is, example, if you take 12570 kilowatt motor, the harmonic current is about 4 amperes. Okay. It's a more case case, one more other income of one where harmonic current is 3.8 amperes. So the point is, the harmonic current coming from the drive, the 4.5 megavolts drive, is just going out to 11 kV and going into the motors. Is just damaging frequently. So the revenue loss for the customer, number one, is significant, and number two, the breakdown in the production line, it's also huge loss for the customer. Reliability. Yeah, independent generators. You know, many it's a practice in many customer players where customers installs backup generators in case the main grid fails. Customers use backup generators to feed the power to the loads. Here is the schematic how the generator works. Let's say I have a diesel generator here. This is the engine and the crankshaft and fed to the alternator winding. So if you switch on the engine, we'll get torque here, and the alternator will pump the fundamental voltage to the load. Let's assume we have the top animation. We have the load of the variable speed drive or maybe UPS. The normal power, 58 power, is going from the alternator and is going towards the drive. You know, the drive is if it is 6-pulse converter, it will pump in fifth harmonic current, negative sequence harmonic current, back to generator winding, and it in turn transfer to the shaft, and we're going to have a negative torque on the shaft itself. So the net effect will be the engine vibrates. The piston actually vibrates in the engine. So when it vibrates, you can see the vibrations in the form of flickerings, in the form of voltage variations, and sometimes generator will stop itself without any indication. So we have this case study in one of the customer where this was the facility of the customer. They have a transformer. They use transformer's main power source, and when if transformer fails, they use DG, 500 kV 2-number DG to feed the power. So whenever they run the DG and switch on the VSD, there is 175 kilowatt 2-number VSDs, DG trips with minor sequence delay. It is sensing harmonic minor sequence and is tripping. So the production loss for the customer was significant. It was one of the critical installation where they were pumping inert gas to compensate carbon monoxide in a steel factory. So without this inert gas, it may become big hazard, safety issue for people living there. So we analyzed the system. This is what we found with the generator. With the generator on, and feeding the VSD, theoretically the harmonic expected was 10% on the voltage side, out of which fifth harmonic was dominant close to 8.5%. So this was causing a big issue, and it was creating negative torque on the generator winding, and it's tripping with negative sequence delay action. So the solution was to have an active harmonic filter at each drives. So the drive will generate some harmonic current, and the active filter senses harmonic current from the drive and will cancel out at the input side. And the net harmonic current flowing in the generator will be sum of 0. So it's been done. Now generator is working without any tripping. Generator is working from past 3 to 6 months, 3 to 4 months is not even single trip after cancelling harmonic in the system. Yeah. So quickly we go through how our flicker comes, how the flicker management, and what are the other issues of harmonics on circuit breakers performance. Yeah, here the facility of one of the automobile factory. They make two-wheelers. One of the biggest factory in, I think, in Asia region. So they have 5 generators. There is no generator. They don't have grid supply yet. So the generator was feeding complete plant in different substations. They have about 12 transformers. All the loads are fed at low voltage, 4 and 5 volts. So we have some measurements. We did the different transformer secondary side. They got the given number MSP 11, MSP 12, so on and so forth. The value you see in the red colors are the harmonics that are exceeding IEEE standards. So we identified there are about 5 locations where harmonics are more. Yeah. The main issue in this plant are twofold. One is the tripping of circuit breakers. They have a microprocessor-based circuit breakers feeding welding loads. There are a lot of spot welding loads in the production line. So at some point of time, the circuit breaker trips. One tripping is causing about 2 hours production outage. So we verified the microprocessor-based circuit breakers will operate on something called DI by dt, or rate of change of current. So if you look at this waveform here, the blue one is the pure AC, and when you add harmonics to this unit, you'll get this waveform which is not sine wave. So the altered waveform will have a different reliability at some point of time. If altered waveform is having a steep rate of change of current, then circuit breaker things fault and tips the breaker. So this was happening in this site. So the harmonic adding the fundamental was creating artificial fault seen by the microprocessor breaker, and the breaker was tripping frequently. So one tripping is about 1 or 2 hours downtime, and this significant loss for the customer. We also had an issue in terms of in the products in the line. They do the welding of chassis. There are a lot of quality rejections in the chassis welding end of the production line. We verified why exactly it happened and the reason for this quality rejections in the site. This is a welding shop arrangement schematic we have. Let's say we have a transformer here and outgoing field going to all single phase spot welding machines. Let's assume the spot weldings are off condition, we'll get full voltage on the bus. That says 400 voltage on the bus. If first machine is on, there's a current flow and there's a drop because of flow of current. Let's say the drop is 5 volts. And let's say the second welding is on. Let's say the drop is again a 10 volt drop is there. So on and so forth. That means if you assume the last welding machine coming into on, it will operate at very low voltage. This low voltage is because of the natural drop occurring across the winding and the corresponding cables. The welding quality it depends on voltage square. The welding quality depends on V square by R of the welding object. So when you have low voltage, you will not get the good quality of weld. So this customer was having a lot of rejection of welding objects at the production line. So we discovered the reason is a huge fluctuation of load that was only for 10 to 11 cycles, electrical cycles. It's about 0.2 seconds. This fluctuation of load was creating voltage flickering and was creating a lot of impact on the quality of weld objects. Yeah. So the solution for this case was to have a centralized post-conditioning equipment that can take care of harmonics, that can take care of huge load fluctuations, and the problem was solved. So we have a sensing at the main transformer secondary side that will sense the complete load on the transformer, including welding loads and harmonic drives, UPS, etc., etc. So the one machine can do the job of all the fault issue that includes harmonics, voltage fluctuations, and reactive power variations, so on and so forth. Yeah. So this is cancelling out here. Yeah, I'm just coming to the end of this session. So how exactly zero sequence harmonics behave in the system? It's critical for building applications where we have a lot of single phase loads, computer loads with SMPS, and so forth. What you're seeing is 3-phase waveform. we have a line 1, line 2, and line 3, and neutral. So line 1, line 2, there is a phase angle difference, 120 degrees, and line 2, line 3 is having phase angle difference, 120 degrees. The waveform, which is just below this line 1, is having 3 cycles, 1, 2, and 3 cycles. It's called third harmonic frequency. So if you compare a third harmonic component in all 3 lines, it's in same phase. There is no phase angle difference between third harmonic current of line 1, line 2, and line 3. So this is called geosequence harmonics. So this harmonic will add up arithmetically, and you'll get almost 2 times. You'll get 3 times the harmonic at each phase. So this is how it is. So harmonic will add up in neutral, and neutral will have huge current compared to phase current. So let's go to case study where we found effect of this geosequence harmonic into in malfunction of circuit breakers and in malfunction of some kind of high-end microscope. Let's assume we have this geosequence harmonic flowing into a cable. This is a cable. This is the cable schematic. It looks like we have a conductor and we have insulation at the both sides. So we can model this cable as the conductor and stay capacitance, right? So this is the capacitance between cable and cable insulation to ground. So this cable insulation capacitance will be spread across the cable distance. So the cable, the impedance, reactance of the cable capacitance is 1/2πfc. That means high frequency means low impedance offered by the cable capacitance. Here we have example. Where we have a microscope. Microscope you used electron microscope using one of the biggest FMCG company. The top image, what you're seeing is the clear image, including the harmonics, and the bottom image is hazy. It's not so clear. So the bottom, both images are from same machine, but when we see they have a UPS feeding this microscope. Also, the same UPS is feeding some out of computer loads also. Whenever you switch on the computer loads and switch on the microscope, you'll get this hazy blur vision in the microscope. And when you switch off the computers, we'll get clear vision. So the high frequency, the harmonic, zero frequency harmonics coming from the computers are going from the computer cables, is going to ground, and from ground it's coming back to this microscope. If you look at the ramp of this image here, the second image, and if you just blow it up, you can see the ramp is having 150 hertz disturbance. 150 hertz is the harmonic disturbance. So from where this harmonic is coming? This harmonic is coming basically from the computer loads that is linked to same UPS on which we have this microscope. The computer loads are pumping harmonics from these cables to ground system, and the ground system is giving feedback to this microscope. So the microscope malfunctions. We have a last case study with us, an IT building. How an IT building suffered with the geosequence harmonic in the system. Yeah. So this is a schematic of this IT building. We have it's a building having 5 floors, 1, 2, 3, 4, and 5 floors, and a basement. Basement, they had 300 kVA UPS, 3 numbers in parallel operation, and output is going to output is a cable, and we have raising vanes from basement up to the top floor, 5th floor, and we have distribution at each floor. We have cable tappings from the main raising vanes going to our distribution boards. Our distribution board is feeding computers, servers, all IT loads in the system. The problem was, in this particular case, they had a earth leakage relay at the output of UPS. They are set to 30 milliamperes for safety purpose. The ELCB was tripping at least once in a month, approximately once in a month. So the PLC bit trips whenever the leakage current from the ground is coming back to EL or leakage relay, which exceeds 30 milliampere set value. So they observe when they run 4 floors, nothing will happen, everything is intact. When they run 5th floor, there is an increase in ground current that is triggering the leakage relay and tripping UPS output side. You know, the tripping of UPS output is critical for IT industry. How UPS trips, output trip, that means the entire IT building is off. There's huge revenue loss for the customer. So we analyzed, this was the analysis we had. Harmonic from distribution board, each floor are coming out and going to raising mains and going back to UPS on the main power cable. But because we had a cable, the cable capacitance was adding in between, and there's a little bit, very small amount of leakage current coming from this cable capacitance, and it's going to the ground, common ground system. And we had a application breaker here at the output of UPS in the basement, and it is adding up at the ground and just shooting into the ELCB and tripping the breaker. So whenever the switch off this floor, the leakage current is about 34 milliamperes. Whenever the switch off this floor, with all the 4 floors on condition, the leakage is about 26 milliamperes. So that means the difference. So this building was having tripping at least once in a month. That is huge revenue loss for the customer, just because of harmonic flowing into cables capacitance. The problem was solved by putting active harmonic conditioners at each dB levels, each floor level. We made sure the harmonic is assured at each levels, each floor levels, and no harmonic came out of this distribution board or cable. So the problem was solved. So till then, no tripping in the breaker. It's safe. Yeah. So this is from my side, Mr. Manasa.
Hello. Hello, are you able to hear me? Hello. Everybody else, I am Jitendra Jain. Mr. Kunjan, are you able to hear me, everybody? Okay. Good evening, everybody. I am Jitendra Jain from Usha Martin. I am just showing one case study done in my company. We are basically producing steel wire rope. Our company is the largest wire rope manufacturer. World is number 2. We have our company has got all kind of means DC motor, AC motor converters for producing wire bars and rods. The plant has got more than 3,000 motors and drives and UPS 4 numbers. As explained by Mr. Srinivasan, you know, I think what is the power quality disturbance. There are some electrical devices in the plant which alter the frequency of sine wave and distort the current and voltage. This distortion may come in different forms. The disturbance can be called dips or swells or notching or impulse oscillated again like this. And if you know the causes of power quality problems, I mentioned on the slide, they are non-linear loads, local resonance, capacitor switching, load switching, etc. Actually, what is the problem due to this disturbance? We, in my plant, we were having high failure of electrical equipment. There were many high breakdown of electrical motors, PLC and drives. So, I mentioned this slide. We were not able to pinpoint the root cause of these electrical breakdowns. There were, there may be many root causes for the breakdowns. Those root causes were addressed one by one, even though the problem not that much reduced. Then we contacted many experts and our engineers. We discussed. Then it was concluded that the quality of power may not be correct. So we should check the quality of power in the plant. So we went for Harmonic study, which was done by some party at Bangalore, Mrs. Ancon actually. After they studied, they found the level of harmonics as you see in the table. The harmonic level and the voltage and current level also you can see the distortion level of this voltage and current also. In the remarks you can see, if you see, take the example of TRF transformer number 7, we were having the level of 37% in current distortion. So we, as suggested by the expert who did the audit in our plant, that we have to go for 10 number of filters for a whole plant. So initially we were not having experience what will be the benefit we will get from having filters, how many filters. So we initially went for only 2 filters. For that we invested around 95 lakh rupees, and we bought actually 2 number of passive harmonic filters from Ancon. After installation of harmonic filters, I just want to share the benefits of these filters. You can see the power consumption kWh per ton was reduced from 173 ton kWh per ton to 153. There was a reduction of 20 kWh per ton. There was a reduction of 11%. Similarly, there was a reduction of in rupees per ton also. We got benefit of reduction in power consumption. That was also around 10.9%. Our production is at the level of 11,000 tons per month. So we got a saving of 12 lakh rupees per month, an annual saving of 1.5 crore. These are the major monetary benefit we got. But if we see the component failure trend, before harmonic filters, installation of these filters, we were having the level of motor failure 33 motors per month, which reduced to 11. And drives, we were having the failure of 56 drives per month, which reduced to 3. Similar in case of PLCs also. So electrical breakdown reduction, there was a reduction of 90 hours per month, which is around 50% of our total downtime of electrical breakdowns. These were the some before after study of harmonic filter. It was when on transformer number 4. The top graph is showing the graph of trend of current, all three phases. before installation of filter, and the lower graph is showing after installation of Harmonic filter. Similarly, one more transformer, number 5. If we see the financial analysis part as shared earlier, there was a net gain of 113 rupees per ton, which lead to 14 means 1.5 lakh 149 lakh rupees per annum. But if you see other benefits, which is related to components, actually maintain and repair something of that kind. The motor failure rate before it was 43. Means it was already shared in the previous slide. That is sufficient. I think it may have different numbers maybe. So we actually, what is the investment we did that give us the payback in 5.5 months. Thank you.
Hello to everybody. My name is M.K. Jain. We have all heard from Mr. Srinivas about the harmonics and how harmonics are produced, and what are the details about harmonics and what are the culprit loads about harmonics. And then from Mr. Jitendra we also heard as to how he has nicely used some filters and case study regarding the implementation of the, some remedies for getting rid of the harmonics and improving the overall distribution system. So now I think we should, after hearing all this, I would like to present make a presentation which talks about how do we ensure that we don't get into these problems right at the beginning, which means basically when we are designing a new system or a new distribution system, whether it is for a factory or a building, how we take care of various design parameters so that we don't get into these kind of problems at the first place. And of course, if we still happen, then there are solutions available. So I would like to take you through this presentation and a brief mention about what is power quality and how power quality okay, so what is basically power quality? If you see this slide here, this shows a series of sinusoidal waves, and we all know as electrical engineers that power quality or power is basically represented by sinusoidal wave. So you see each of these wave here has some kind of a aberration or some kind of a problem, except in the last one, which is a perfect power, which is a sinusoidal wave, which is what Mr. Srinivas had also shown in his presentation, that yes, this kind of wave nowadays is visible only in the laboratory and will not see in the practical basis. But before we go into the various design parameters as to how do we implement the design parameters so that we don't get into these problems, I would like to take a little holistic approach about the entire PQ. Yes, we always talk about harmonics when we talk about PQ, but is harmonics only the PQ problem in India, in a country like India? In India, we have many other basic problems of power quality. The very basic being that we don't have power cuts. Those are the basic problem. Then there are voltage fluctuations, there are frequency fluctuations, there are power cuts, there are load shadings. These are also the problems of power quality. And of course, the most talked about problem is the harmonics or the transients that we are. These problems are, as we all know, are taken care by the industry generally by using various well designed and well used solutions like generators, UPS, voltage stabilizer, surge protection devices, all of these, and even capacitors for micro cuts. All of these well designed systems are already available and are being used and should be used predominantly to take care of the power quality issues. But even after taking all of this into account, if we still have the power quality issues or power quality problems from bad power quality or a bad quality of sinusoidal wave, that is harmonics, then how do we go about it, and what are the problems that we face because of that, and why it is so important? Because most important thing about this harmonics and their effect on the industry and on the general is that it leads to a lot of breakdown, and continuity of the production gets suffered. Breakdowns of IT equipment can happen, such as PCs and servers, or stored machines in factories can result in idling of manpower, loss of production resulting in millions of rupees in the factories and IT facilities. And most important is the fire safety. In a building or in any industry, the fire safety is most important. And to reduce the fire risk, good quality of initial electrical design and maintaining high power quality throughout during operation of the electrical distribution system, whether it is for a factory or for a large building, these are very, very important. How do we overcome this power quality? As I told earlier, if it's a power cut, we can use generators and UPS. If it's a small micro cut, nothing is needed. The capacitors present in the system take care of that kind of a problem. The voltage fluctuations are taken care of by stabilizers. Frequency fluctuations again by using UPS. Transients are taken care of by S3Ds and TVSs. And harmonics, as we have already heard about it, unlike the other problems that we just mentioned, these are the problems that a user gets from the grid. When he gets power supply into his premises, these problems comes along with the power supply, incoming power supply. But this harmonics is something which is self-generated within your system, and therefore it has to be self-cured. And a good design and continuing with that design during operation of during the maintenance and operation of the facility will ride you through a problemless situation. Typical loads in a buildings are always microprocessor based elevators, escalators, then HVAC loads such as AHUs, pumps and compressors. They all use variable frequency drives, light fittings with electronic ballast, BMS systems such as fire alarm systems and CCTV and access control systems, IT equipment such as desktop PCs, servers and switches, UPS and DC power supplies, AV equipment such as projectors, LCDs and audio systems. Now all of these loads are basically harmonic rich in nature. They produce harmonics, and most predominant and the large size loads are variable frequency drives and UPSs. Now if you see a typical power distribution system of a building, you can see here that there is a transformer, there is a generator as a backup source, and then there is a lighting and air conditioning in a building, and there are computers and telecommunication loads, and there are PLCs if it's an industrial facility. So you can see that in any distribution system there would always be a presence of harmonic producing loads. And these are, you already seen these, that how the harmonic waves get distorted. I'll skip through that. What are the economic impact of these harmonics? Higher losses in transformers, motors, cables, increases bills, monthly bills, breakdown in CNC machines, increases production loss, nuisance tripping of breakers, again production loss, overheated cables and terminations leads to production loss, genset failure to start also gives rise to production loss, failed transformer, production loss, lower power factor will give you a penalty in the tariff, And higher THD will also give you penalty, as Mr. Srinivas had shown in his slide, that some of the electricity boards are already gearing up to levy penalty on the consumers who are injecting harmonics into the grid. And all of this reduces the service life of equipments, and which requires early replacement. In fact, it has been seen that reduction in life is estimated to be about 32% for a single phase machines and about 11% for three-phase machines, due to only, and 10% for transformers, only due to harmonic effects. So if these harmonics can be minimized, and if remedial measures can be taken, either retrofitted or initially during the design, we stand to save a lot of great losses. Now, how to avoid these harmonics and how to go about designing a new system where these harmonics are either avoided or minimized. So basic design features have to be targeted towards minimizing the effect minimizing the harmonic producing loads at source, isolating and arresting the harmonics, filtering and absorbing the harmonics, and last but not the least, oversizing the cables and equipment. And operation, this is design features, and operation features when people are in charge of FM facility maintenance in buildings and maintenance departments in factories. They should check for overheated neutrals and check for undue heating in the cables. These are telltale signs of effects of harmonics in any distribution system. And of course, failures of unexplained failures of motors and many machines. Now, how do you minimize at source? When you are deciding a new facility and you are planning new distribution system, the equipments and the loads that you select, and I am mainly discussing about the buildings, new buildings and commercial buildings and a lot of office complexes and IT facilities. What you can do there is select the UPS and VFDs. These are the two main large loads which are present in any building or even in factories nowadays, and these have to be selected at the beginning with these two parameters in mind, that the input THD drawn by these equipment should be less than 5%, and the power factor of input power drawn by these equipment should be higher than 0.95%. Now, UPS and VFDs, variable frequency drives, are very much available in the market with these features and without these features, and therefore the purchaser and the designer and the user has to be very, very careful that he selects these two equipments with care, and he insists on these parameters while purchasing these equipments. Yes, the cost of purchasing with these two features would be higher, but yes, the high cost will have to be offset against the elimination of future problems. Then of course there are, in IT industry, there are servers which should be bought with less than 3% harmonics, which are already available. In fact, all servers and everything is available with these kind of things. Electronic ballast, again, nowadays they are available, they are present in large number, both in buildings and in factories. And they are also sometimes a cause of heavy harmonics, because a cheaper designed ballast or a choke will give you as high as 33% harmonics, and a cumulative effect of 1,000 number of light fittings could be a very large effect on a transformer, on your transformer. And therefore this also one has to take care that when you are buying new light fittings or you are retrofitting light fitting with power saving CFL lamps or now even LED lamps, make sure that the LED drivers or the ballast of CFL
बॉस क्या प्रॉब्लम आपका चलेगा?
अभी रहेगा मुझे घंटा
रहेंगे
मिलेगा।
हाँ तो पुत्र आप डिनर को भी नहीं आएंगे, आपको डिनर को
वहाँ पे क्या
Hello? Okay, so I was talking about use of special equipments for arresting harmonics. UPS itself is a nice, is a very well designed equipment which will arrest your harmonics from the loads that are connected to UPS, because all the UPS which are used nowadays in IT industry and even in factories, they are online UPS, and they convert the entire power into DC and then reinvert, and therefore UPS itself arrests all the harmonics which are coming from the load connected to UPS. Although UPS itself produces harmonics, but nowadays the new generation of UPS is producing very low amount of harmonics, never higher than 5%. Then there are these PDUs with delta star isolation transformers which can be used to arrest harmonics which are being produced by any of the SMPS based loads. Then there are zigzag and phase shifting harmonic cancelling transformers which can be used in various installations including factories. And there are dual and quad output transformers, and there are passive and active filters that can be used, which were earlier also spoken as a case study, and they have been used very effectively. UPS, when you use, you can see in this slide that if the harmonics in the load towards the electronic loads and computers and servers, it could be anywhere between 70 to 100%, but a UPS will reduce it effectively to somewhere between 3 to 30%, depending on the kind of UPS that one is using. Then there are these transformers, isolation transformers, and various types of them, which could be used to arrest the harmonics at its source. Many times there are problems of CNC machines in the factories, and sometimes even in the IT industry there are problems which are being faced due to harmonics. So depending on the nature of harmonics, and you can, after studying the type of harmonics, one could use a particular and a special kind of a isolation transformer and the phase shifting transformers, which could result in total elimination and arrest of the harmonics at that level without spreading to the entire network. Then one can use, you can see from this slide here that the reduction in the harmonics by use of these special transformers could be anywhere from prevailing 37% to around 10 to 13%. So there is a significant reduction achieved by using these transformers. Then there are passive filters, and one could even use the active filters. Passive filter network is again a designed filter network, RC, RNs, RC and L elements, which could take care of known harmonics. If you know what are the harmonics in your systems, you could use a well-designed passive filter. But at the same time, if you are not very sure and the nature of your loads are varying and your harmonics are also varying, then one could use an active harmonic filter and connect it just like a capacitor panel that we connect to our main panel. And this active harmonic filter will arrest all the existing harmonics, or eliminate or cancel all the existing harmonics in your system, because this harmonic filter will produce exactly opposite reverse of the harmonics which are available in your system, which are present, and will cancel all the harmonics. Then very simpler methods which can be deployed in existing situations is a full size or a double size neutral. This again is applicable to mostly triplan harmonics which are prevalent in SMPS based loads, where The zero sequence harmonics that we were earlier saw are basically flowing through the neutral. All the three phases harmonics will get combined and flow in the neutral, and therefore sometimes one would find a neutral current higher than the load current, which is a very strange phenomenon. These kind of IT systems where these triplet harmonics are very large in number, and here one has to resort to using a double size neutral. We generally use either a full size neutral or a 4-core cable, what we call, or a 3.5-core cable, which is known as reduced neutral. But in these kind of loads, we may resort to, or rather it is a very standard practice in IT industry to distribute the power, UPS power, to various computers and servers using a double sized neutral, so that the neutrals do not get overheated. Then derating of cables can be done. So, a cable which is meant for 300 ampere should be used only for 200 ampere or lower, so that doesn't get overheated due to the various effects of harmonics, including skin effects and things like that. Similarly, the transformers and generators have to be derated. So 1000 kVA transformers cannot be used beyond 700 kVA if your loads are harmonic rich. So these are simpler methods of doing that if you already have harmonics in your systems. The earlier methods that I had spoken of was basically implementing a new system or a new design. If you are designing a new system, and if you are taking care of all of these features that I discussed, the increase in the cost of the electrical distribution system will only be around 60% if all of these measures are used and implemented at the time of initial installation. And the cost of retrofitting the system with these things would be not less than 40%, and therefore you can see the advantage of doing this at the time of initial installation or initial design itself. There are no standards in India for governing or controlling the harmonics or deciding as to what we should use, but for USA there is a very famous IEEE standard 519, and for Europe there is IEC 555 and IEC 1000, and Indian standard is about to be released, and I hope it will be available next year. Thanks.
Thank you everyone for your patient hearing. Please submit your questions. This question is to Mr. Srinivas. Do our electricity regulations allow distribution utilities to penalize ST customer? Please do respond.
It is India. If it is India, yes, there are some utilities. They are already implementing harmonic regulations for 11 kV and above consumers. For example, South India, they have in Tamil Nadu and Andhra Pradesh, they already just given some kind of letters, but it is not enforced yet. But the purpose is to enforce these regulations in a very near future.
And the second question in that sequence is, does the existing energy meters measure the same?
Good question. Energy meter, if you go with the normal magnetic energy meter, the disc will rotate in reverse way. Okay, if you have a fifth harmonic current flowing into this particular energy meter, that's magnetic based energy meter, the disc will rotate in reverse. But if you go for electronic energy meter, it will not be able to record it actually.
Okay, there is another question which is how would the metering system to monitor harmonics be implemented, metering which is affordable and easily monitored. Affordability is the key in large-scale deployment. While in Malaysia we have some debate on implementing tariff structure or penalties for Harmonics, the practicability and financial viability, not to mention political implication related to any cost addition for the power sector, is still being debated. This, I suppose the question is from Malaysia. So practicality of harmonic metering from the utilities revenue side, how it can be addressed?
Okay, so there are two ways to address this. Number one, nowadays we have a lot of instrumentations where we have inbuilt THD recording and trending of THD as well. All right. So we can take this data and wire it to SCADA or software and convert this to reasonable figures like THDI, THDB levels, so on and so forth. That's number one. Number two, in some part of the world, utility are hiring their own contractors. That means the contractor will come with their harmonic analyzing instrument. They'll go to consumer place. They'll go to the 11 kV metering point. They measure the harmonics and give the report to consumer, also to utility. Okay, there are two ways that they're doing in many parts of the world.
Just to supplement, here in India, there is a provision called ABT metering, availability based tariff metering, in which the THDV and THDI can be captured. Only trouble is that if you want to do the data logging, then that metering can become little costlier. So from the affordability point of view, the data logging is an issue, but to get a snapshot, to get the position of the THD in customer's place, the affordability of meter is already in place. So we move to the next question. I think this is for Mr. Jitendra Jain. The question is this, was the kilowatt hour per ton savings after capacitor for improvement of power factor or after implementation of harmonic filter?
No, it was only because of harmonic filter. Because earlier also we were having 0.96 or 0.95 power factor, and after having the filter we reached to 0.97, not much improvement in power factor. Okay.
Great. Okay, this is another question to Jitendra ji. Considering various small and medium type industries, what minimum PQ solutions can be adopted by them? What ROI is to be expected from it?
To be frank with you, Mr. Manas, I cannot be predicted because it depends on the kind of irregularities or the disturbance in the quality of power in each industry. Either it is small, whether it is big. So investment cannot be predicted based on the connected load of the company, or we cannot say it is neither for a small industry or big industry. So for going through the right solution, first they need to go for some audit kind of thing. They should first examine the quality of power which they are getting. Only through that they can they can see some solution. Okay.
Maybe I can little bit supplement further. One of the key things which the small and medium scale industries they can adopt is the right kind of reactive power composition into harmonic rich environment. And if they can assess that, and then they adopt the right kind of filtering rather than only capacitor, but capacitor reactor combination and right kind of sizing of equipments, as Mr. N.K. Jain pointed out in his design aspects. probably you can save some trouble. And depending on the economic loss, the ROI has to be assessed. But normally we have seen in most of the cases, you can get your investment back before 2 years. We have no more questions. You are welcome to send email and questions, and we'll be organizing to reply. And we thank you once again for a good evening. Thank you for participating.
Thank you. Bye-bye.